a talk on the historical construction of normativity in mathematics. For a little bit of background, I'm a hobby scientist and I study mainstream economics in unconventional places. For example, I have a preprint out with Mike 11 about the economics of collective intelligence, where we observe that the bioelectric communication system that exists between cells is analogous to the price system that human agents use to coordinate with each other in the economy. So what I do is I take totally standard mainstream economic ideas and I find them in places where you wouldn't ordinarily expect to find them, such as biological systems, or in this case, Platonic space and mathematical structure. So what I'm going to argue is that Platonic space has economic structure. I've already made some arguments like this in the past. I have a talk on Michael Evan's channel called Agency at the Very Bottom, where I observe that mathematics has some of the properties that you'd associate with an economic agent. I also have an essay on my website, benjaminflyons.com, called 2 Examples of Memory in Math, where I show that mathematics engages in efficient confabulation, that hallucination done in a certain sensible way is actually a very important part of mathematics. And I have the essay Normativity and Timeless History in Mathematics, available at my blog, interestingessays.substack.com, where I talk about normativity and timeless history. This talk is basically just an expansion of what's in that essay. Where I get these ideas from is by studying scientific structure and then working backwards to see something analogous in mathematics. So all these ideas are really based on my study of the historical construction of normativity in science, where I've made a number of observations. The first is that normative properties are constructed, not evolved or otherwise prescribed. So the source of values in a human agent or any other kind of goal-oriented system are actually constructed within the system as it basically navigates the world. They don't come from evolution. They're not in any other sense pre-built into the system. What normative properties are preference orders over positive facts. So basically you have a selection of objects. The normative properties pertaining to those objects are about how they are ordered with respect to each other, specifically forming what economists call a preference order. Those facts themselves are the peaks of preference orders, so the normative positive divide, although sometimes useful, is not in fact fundamental. And the preference orderings over those positive facts are constructed through historical processes. Now, in the context of science, what I mean by historical processes is more or less what you'd imagine a sort of past and history leading up to the current present moment. As we'll see when we talk about history and mathematics, we mean something a little bit more general, where the concept of time does not really apply, but we'll discuss this later. Some background ideas as well to provide some context for where this is coming from. I draw some ideas from the following sources. The first, of course, is economics. The second is the theory of constructed emotion, created by Lisa Feldman Barrett and her colleagues. There's also the dynamic systems theory of Esther Thalin and her collaborators. So, of course, the collective intelligence work that Mike does. I have various relevant essays on this subject, again, at my blog. 2 of the most critical ones are Abolish the Value Function, Constructing Values Through Metabolic Processes, and How Economies Work Out Their Ises and Their Oughts. So if you're looking for some more context and some of the more scientific background behind this talk, feel free to check out any of those sources. So what are we going to do in this talk? Well, mainly what we're going to do is work through 2 very simple examples. Mostly we're going to be talking about the Cartesian product. The bulk of this talk is just working through a very simple but very important example of how the Cartesian product works in mathematics. We'll also briefly talk about the natural numbers, because the concept of history is very clear when you're talking about the natural numbers. And we're going to see a few very interesting and important ideas. The first is that mathematical definitions are pointers to solutions to optimization problems. Mathematical definitions don't really tell you what something is. They hint to you, the human reader or human listener, as to how to construct a solution to an optimization problem. And we'll see that the process of constructing a mathematical solution is historical in a way that we'll explain later on in the talk exactly what historical means in this context. And so what we'll see is that mathematical definitions are inherently normative. They're about what's best for solving a problem. And so what I'm basically trying to demonstrate here is that normativity is really built into mathematics itself. It's not something that comes along later when a human being with a brain decides to value something. It's something baked in at the mathematical level. So with that all in mind, let's start with our example of the Cartesian product of two sets. Again, this is going to be most of what we're talking about, just how this example works. So we're going to consider two sets here. The first set is the set A, which is going to consist of two elements, A1 and A2. It's a very simple generic two-element set. And then the other set we're going to think about is B, which is going to be another generic two-element set. We'll say that the elements are B1 and B2. The details of A and B don't really matter. It just matters that they each have two elements, and we're just going to keep track of them very simply with A1, A2, and B1, B2 for A and B respectively. Given these two sets, the Cartesian product is defined as the following set. The set is labeled A times B. That's one set, A times B, and it consists of the following four elements. The way these elements are constructed is you take a component from A and you pair it with a component from B, such that each element of A is paired once with each element of B. So we have the four elements A1, B1, A1, B2, A2, B1, A2, B2. We treat them as ordered pairs, so they're each contained parentheses, and then each sort of parenthetical element is separated by a comma. So there's a lot of stuff being written here, but this is a four-element set, which is very important. So this is the standard definition of the Cartesian product. Many of you might be familiar with it. You'll see it in many an introductory math textbook. However, there's something very weird about this definition, which is that this Cartesian product, although we've written it in a very elaborate way, it's in fact isomorphic to a generic four-element set. So let's just say the set containing the elements W, X, Y, Z. Both of these sets are isomorphic to each other because this set is just a four-element set, and this set is also just a four-element set. So if these are both four-element sets, why is the one on the left a Cartesian product and the other isn't? They're isomorphic to each other, so we should expect them to be the same, and yet somehow we're thinking of them like they're different. In order to do this, we need to understand the real definition of the Cartesian product and how it's actually a normative definition about trying to solve an optimization problem. The real definition of the Cartesian product is that the Cartesian product of the sets A and B is any set that fills out this graph in a particular way. So on this Cartesian plane, we have the A dimension consisting of just the nodes A1 and A2, and the B dimension consisting of just 2 points B1 and B2. And together they form a Cartesian plane consisting of these four coordinates denoted by the little black circles. And the real definition of the Cartesian product is that we're trying to solve a problem, which is how do you fill out this graph in an efficient way where each node is filled out once and only once. So I'll give you an example of what that looks like that will hopefully clarify. Just looks like this. So to each of these nodes, we assign one and only one element by a function, so no element is used twice. So at the node for the coordinate A1, B1, we assign obviously the element A1, B1. At the node A1, B2, we assign obviously the element A1, B2. Same for the node A2, B1, and the node A2, B2. We assign one element and only one element to each of these four coordinates. This is what it really means to be the Cartesian product. Now what we need to do in order to further understand this definition is to clarify what it means to assign a point to each of these coordinates. And the way we do so is with functions called projection functions. So let's call those functions f and g. We can consider f to be the function that takes one of these coordinates and maps it down to the a dimension, and g will be the function that takes these coordinates and maps it to where it corresponds to on the b dimension. So a1, b1, for example, the f function would take us down to a1, and the g function would take us over to the left to b1. So it's really these functions that tell us how we've assigned where these coordinates are. We're not simply relying on visual intuition. We can actually definitively say with functions what it means for each of these elements to be assigned to the point that they're at. And we can just clarify this with a little bit of mathematical notation. F is a function from the Cartesian product to the set A, going down like this, and g is a function from the Cartesian product to the set B, going over to the left. And what we have assigned here is we're just simply taking the A element of the Cartesian product, sort of the A coordinate, and assign, or A component, I should say, and assigning it to where it is in A, and then assigning, the B coordinate to where it is in B. So everything just works in the most intuitive, obvious way you'd expect. And what is going on is the functions are telling us which node each element fills out. So we can use the graph to understand what's going on, but it's really functions that tell us exactly where each point is. The functions are what sort of makes the graph mathematically precise and meaningful. And that's exactly what we see here. What this means, what does it mean for A1 comma B1 to be assigned to this point? It means we have a function f taking this point to its A component and a function g taking this point to its B component. So what we can see here is that the Cartesian product is really a solution to an optimization problem. Our optimization problem depicted on the left here is how do we fill out the Cartesian plane in an efficient manner? And on the right, we see the optimal solution, which is to take a 4-element set, because we have 4 points, we want a 4-element set, and assign a unique element to each point such that we filled out each point once and exactly once. Optimization problem, optimal solution, that's the real definition of the Cartesian product. To understand what's so optimal about this, we can consider some suboptimal solutions. Let's consider a 3-element set. Say the set, let's just call it D, and let's say it consists of the elements A, B, and C. Then as you can see, what happens if we try to fill out the Cartesian plane with this 3-element set, one of the points necessarily needs to be left unfilled because we only have 3 elements and we're trying to fill 4 points. So if we're using a function to fill these out, well, a function can't use an element twice. So a 3-element set would be a suboptimal solution to this optimization problem. Another suboptimal solution would be a 5-element set. So let's say we have the set E that equals A, B, C, D, E. Then this set would necessarily have to fill out one of the points twice because we'd be trying to use 5 elements to fill a 4-point graph. So this is also a suboptimal solution. Another suboptimal solution, a little bit more subtle, is that we could have a 4-element set, but we could misuse it. We could sort of misapply what it's supposed to do in this context. So if we consider a set just consisting of the 4 elements W, X, Y, Z, we don't necessarily have to assign all of these 4 elements to one of the 4 different points. We could assign all of them to the same point, for example. And so we have 4 elements for 4 points, but we're not using it to properly fill out the Cartesian plane here. So this is also not an optimal solution. And this is really the most important example because it shows us that what's important here isn't simply having a 4-element set. It's how you use the 4-element set that matters, and how we use that set is really denoted by projection functions, which here we're simply indicating with the position on the graph. So with this in mind, let's summarize what we know about the optimal way to solve our problem here. Our goal is to fill out the Cartesian plane, all 4 elements. We do so optimally by assigning, taking a 4-element set with a function that assigns a unique element to each point. What it means to assign an element to a point is to have these projection functions, f and g, telling you where you are on the A dimension and where you are on the B dimension. We have the formula for those functions over on the right there. And a very general and very important way of depicting this situation is with the following graph. So what this is just saying is we have a set A times B, that's our Cartesian product. And what we're saying is we have a projection function to F and a projection function to B, projection function F taking us to A rather, and a projection function G taking us to B. And this is a very generic picture of what we have above that's a little bit more general because it doesn't really specify that we're working with a 4-element situation. So this chart here down on the bottom is very important. We're going to come back to it in a bigger way later. Now, there may be something you might have noticed, which is that the Cartesian product A times B isn't the only set that can function as the optimal solution to this optimization problem. Any 4-element set can be used to fill out the Cartesian plane in the appropriate way, so long as we do so correctly. So we can take our set W, X, Y, Z, and as long as we use it in the way that makes sense, rather than assigning everything to just one point, we can solve the problem just the way that the Cartesian product A times B can. Here is what our projection functions look like. Let's call them J and K. And what they're doing, there's a lot of information here, but it's all very straightforward, works exactly the way you would expect. So W here What we're saying is there's a function taking it down to A1. That's what this means. W is being mapped to A1. So that tells us where we are in the A dimension. And then there's another function, which we'll call K, telling us where we are in the B dimension, taking us over to B1. So W would get mapped to B1. And this is how it works for all of this. So what's X over here? Well, it's being mapped to A1 because that's where we are. And then X is being mapped to B2 because that's where we are on the B dimension. So this all works in just the most obvious way you'd expect. So this denotes what J and K look like here. J is taking you down to the A dimension. K is taking you over to the B dimension. And again, we can have this little chart down here just showing us the very general picture. We have a 4-element set, W, X, Y, Z, with a function J taking you to A and a function K taking you to B. So if we compare the situation here, we can see that they're both doing the same job. Both A times B are official Cartesian product, and the generic 4-element set W, X, Y, Z, each of them has a 4-element set. Each of them has functions, projection functions taking them to A and taking them to B. We've called the functions A times B. Its functions are F and G, whereas W, X, Y, Z, it has the functions J and K, but obviously the labels don't really matter. Should be intuitively obvious that what the functions do are identical in each case. So we should ask ourselves the question, is there a more formal way in which we can compare what A times B is doing to what W, X, Y, Z is doing and see that they're doing the same job? That comparison would be done with a function. So is there some kind of function between these two sets that denotes what should be intuitively obvious, which is that they're all doing the same job here? Both of them are functioning as optimal solutions to our optimization problem of filling out the Cartesian plane. In order to do that comparison, we're going to do it in the most obvious way possible. So what we have depicted here is how each of our two sets are doing the optimal job of filling out the Cartesian plane. Over on the left here, we see how A times B is doing it. Over on the right here, we see how W, X, Y, Z is doing it. And here are those projection functions reminding you what it means for the points, for the elements here to be assigned to each point of the Cartesian plane. So with this in mind, we can just do a comparison. Let's take the comparison A1 comma B1 and compare it to the element W over here. Visually, it should be obvious that each of them is performing the same role. They're each filling out the point at A1, B1. But how do we show that a little more formally? The answer is with function equality. So if we take our function f that takes this point A1 comma B1, or this element, and maps it down to its A dimension, that brings us to A1. So f A1 comma B1 equals A. Well, if we consider what J does, J is the function that takes this W element down to its A1, takes it down to where it is in the A dimension, we can see that it's also taking it down to A1. So we can see very obviously, just visually, that f A1 comma B1 equals A1, which equals JW. So we're seeing that there's a very clear formal sense in which both of these are filling out the same place along the A dimension. And then we have exactly the same thing for the B dimension. So there's the function g taking A1 comma B1, this is g, and takes it over to the B1 point where it's at. And similarly, k takes us over to the left here on this side. K would take W to B1 as well. So what G is doing to A1 comma B1 is exactly what K is doing to W. So we've got different labels for everything, but through function equality, we can see that all we've done is change the labels. A1 comma B1 is doing exactly the same thing that you would expect that W is doing. And the same, of course, is true for all these other points. With the exact same kind of function equality argument, we can see formally that X is doing the exact same thing as A1 comma B2, that Y is doing the exact same thing as A2 comma B2, and Z is doing the exact same thing as A2 comma B1. All we're doing is changing the labels. Nothing else is different. So we can depict this even a little more literally by considering a projection function between W, X, Y, Z to the elements of A times B. So if we were to consider a comparison function, we can see very clearly that W would map onto A1 comma B1 because we can see they're in the same points. That's what these two graphs are showing, where all these points are. So W should obviously map to A1 comma B1. X should obviously map to A1 comma B2, so that's what this arrow means. y should obviously map to a2 comma b2, and z should obviously map to a2 comma b1. So we're trying to compare what these two sets do with a function, and this is exactly what mapping our function should do. And you should notice that it's an isomorphism. So it's not just any old function, but specifically it's a one-to-one and surjective function. So we can just indicate that it's an isomorphism by just putting the I on top of the map. We're not just comparing these things with a function, but we're comparing them with an isomorphism, and moreover, a unique isomorphism. There's only one isomorphism between these two sets that depicts how each of these elements are being used to do the same job. So between two 4-element sets, there's 24 generic isomorphisms, but given how we've chosen to use the elements of these two sets to fill out the Cartesian plane, there's only one isomorphism between them that preserves that common use. So not only are they isomorphic, but they're uniquely isomorphic. So if you think of isomorphism as meaning they're the same, then unique isomorphism means they're really, really the same. So we can go back to our comparison chart here and see this depicted a little more formally. Both a times b and wxyz have projection functions to a and to b respectively, and denoted with this dashed arrow with an I, there is a unique isomorphism from wxyz to a times b, denoting that they do the same job. And the formal conditions for saying that they're doing the same job are these two equations. So the way we read this is we say j, this function taking wxyz down to a, is equal to, does the exact same thing as the way we read this is it's f follows I. So first you do I, so taking wxyz to a times b, and then you do f. So what we're saying is we can either map directly from wxyz straight to a, or we can map wxyz down according to the unique isomorphism that we specified and then go over to a, and both of those things are the same thing. So it doesn't matter which direction we go, you're going to end up at the same place either way. And the same is true of this equation over here. What it's saying is that we can either go directly from wxyz to k through k to b, or we can go down I, g follows I, that's what this little circle means, and then we end up the same place either way. So what it's telling us is it just doesn't make a difference which way we go. There's unique isomorphism that keeps everything the same. So we can see this just to be a little more explicit about exactly what's going on. I want to make sure there's no possible misunderstanding about this. It's very important. Let's consider a specific example, say the element w in wxyz. Well, these two functions j and k tell us how we're using w to fill out the Cartesian plane. So j is telling us that w is located at the a1 point on the a dimension, and k tells us that's located at the b1 point in the b dimension. And that's also what f and g are doing for this particular element a1 comma b1 in the Cartesian product a times b. F is telling us we're again at the a1 point, and g is telling us we're at the b1 point. So that's where these two are. And obviously what we can see is that if we take w and we map it through j to a1, that takes us to exactly the same place as mapping w to a1 comma b1 and then following f to a1. Doesn't matter which route we go, we're going to start at the same place and end at the same place, so those functions are equal. And the same is true of going to b. We can either map w through k to b1 directly, or we can map w to a1 comma b1 and then map it through g to b1. Doesn't matter, we end up at the same place. So there's a very clear literal sense in which these two sets can be used to do the same job here, and we sort of formally compare them with functions in this unique isomorphism. And so here's what those equations look like. What we're just saying is jw equals a1, that's what this means, a1 and a, which is the same thing as f follows I, so I taking in w takes us to a1 comma b1. That's what this means over here. So iw turns into a1 comma b1. That's how we've chosen our mapping, and then that gets taken to a1 as well. And the same thing for going over to b here. So this is just making it very, very explicit and sort of elaborating on this very simple but very important example of what exactly it means to use these two different sets to do the exact same job. So all that we just went through with all these functions is just a fancy way of describing the obvious. Like this should in fact be very obvious, which is just that all this is saying above is that we're using w to be located at the same spot on this plane as a1 comma b1. And we're using x to be located at the same spot as a1 comma b2, etc. All these functions and all this notation, it may look a little bit complicated. It's just a fancy mathematical way of saying we have used each of these sets to fill out the Cartesian plane in a particular way. And given those particular choices about how we've done so, there's one exact obvious way to compare these two such that we can say we've done the same job with them. So with that in mind, we can go back to our original question, which is that something was weird about the definition of the Cartesian product, which is that we have the two-element set A equals A1 comma B2. We have the two-element set B equals B1 comma B2. And then again, the Cartesian product is A times B, which then equals this four-element set consisting of these four ordered pairs. And what's weird about that is that this is isomorphic to any kind of generic four-element set. So why do we normally get told that the one on the left is the Cartesian product and the other one isn't? Now we have a clearer answer to this question, which is that the set A times B equaling these four ordered pairs never actually defined the Cartesian product, because what the Cartesian product actually is filling out that Cartesian plane, and this set in and of itself does not intrinsically fill out this Cartesian plane. It's just a set. We haven't actually applied any functions to it yet to fill out the Cartesian plane. So what this set is actually doing is it's just written in a way that allows a human reader to intuitively figure out how to use it to be the Cartesian product. In other words, it's a pointer that allows an agent to figure out what to do. It's not really defining the Cartesian product in the traditional sense. It's making it obvious for you how to construct that definition. This is why any four-element set could be the Cartesian product of A and B if properly used, because it's not really about this specific set with its four ordered pairs. It's about using it properly on the Cartesian plane. The proper use, again, just means filling out that Cartesian plane, which means the functions that we just saw, a function assigning each node one and only one element, which is why only a four-element set can be the appropriate Cartesian product or do the job of the Cartesian product. So what really makes the set A times B special is that it essentially acts like a guide. It's kind of like the North Star. It gives you an intuitive means of comparison for whether you're using a set to be the Cartesian product correctly. So let's look at that comparison. So this is basically just a slightly more generic version of what we saw before. Instead of specifying specifically the set W, X, Y, Z, let's consider any generic four-element set S. And let's say that it's got two functions, one to A, one to B, and let's just call those functions 1 and 2, it doesn't even matter. Then the really real definition of the Cartesian product, A times B, is that A times B is the set that helps us perform this comparison. Where what we're saying is that if we've used A times B to properly fill out the Cartesian plane, then any other set S that also properly fills out the Cartesian plane must necessarily be a set with a unique isomorphism I to A times B, such that we have these two conditions here, which basically, again, just means that just going from S to A is the exact same thing as mapping S to I and then to A through F through this unique isomorphism. And the same thing is going on the B side over here. This is just a fancy way of saying if we use S to fill out the Cartesian plane in a way that's analogous to how we've used A times B to fill out the Cartesian plane, there's unique isomorphism between them, and A times B, the Cartesian product, is really just our sort of ideal template for comparison because it's very easy to use that comparison. That's really how we define the Cartesian product. So with all of this in mind, we can see a number of interesting things about the definition of the Cartesian product that might not normally be obvious. The first and most striking is that the definition of the Cartesian product is goal-based. It's not exactly some logical derivation in the ordinary sense. Instead, what we're doing is we're saying we have an optimization problem, which is how to fill out a Cartesian plane in a certain ideal way, and the Cartesian product is the set that does so. Something else that we can see is that the definition of the Cartesian product is relationally real. There's nothing about the set itself that's intrinsically a Cartesian product or not. It's about how it's used. It's about its relationships with the sets A and B that tell you if it's actually the definition, if it's actually the Cartesian product. Something else we can see that the Cartesian product is that the Cartesian product is multi-causal. This is a term from Esther Thalin, which basically just means that if you ask, where is the property of something being the Cartesian product? Is it in the set itself? Is it in A? Is it in B? Is it in the relations between them? The answer is it's all of the above. It's everywhere all at once. It's not stored in any particular location. It's when the entire system is assembled the way it is, only then you have the Cartesian product being that way. It's almost like a collective intelligence. You can't attribute the goals or competencies to any particular part. It's within the entire system. The Cartesian product is also polycomputable. A set can be the Cartesian product and not the Cartesian product simultaneously, so you can ask it different questions and get different answers all at the same time. We'll discuss all of these more in subsequent slides. And it's finally historical. We're going to need to define that by using a natural numbers example, but first I'll just explain how the Cartesian product is goal-based, relationally real, multi-causal, and polycomputable, and then we'll talk about history. So to begin with, to see how the Cartesian product is goal-based, normally we're told that the definition of the Cartesian product is that it's this 4-element set consisting of ordered pairs on the left here, but actually what we've seen is that the real definition of the Cartesian product is about filling out this Cartesian plane on the right in a certain appropriate way. So this is actually not the definition. This is the actual definition, or sort of a template for the definition. So the definition of the Cartesian product is not about writing down mathematical symbols in a proper manner. It's actually about solving a problem. So we define the Cartesian product with respect to our goals, and that's exactly why a set like W, X, Y, Z can be considered the Cartesian product. Even though we're not writing down the symbols the way our math textbooks tell us to, we can still use this set to fill out the Cartesian plane and therefore be the Cartesian product. And that's exactly what we've seen, which is that we can use either of these two sets to fill out the Cartesian plane in an analogous way. And we sort of formally show this by saying there's a unique isomorphism between these two sets in terms of how we use them. So again, there's 24 generic isomorphisms between these two sets, because that's how many isomorphisms are between two 4-element sets. But in terms of specifically how we've used them to fill out the Cartesian plane, then W has to be mapped to A1, B1 specifically, Z has to be mapped to A2, B1 specifically, X has to go here, A2, B2 has to be with Y specifically. So there's one isomorphism that says we've used these in the same way. The Cartesian product is relationally real, which means that it's defined in terms of relationships. There's nothing about the set A times B in isolation that makes it the Cartesian product. Instead, it's the relationships between A times B and A and B, and also S. It's really this unique isomorphism with these conditions here that really makes A times B the Cartesian product. So it's all about relationships, not about the set itself. The Cartesian product is also multi-causal. So again, the A times B set is not the Cartesian product until this whole system is in place. The Cartesian product is not stored in any one part of this system, but it's something that is assembled or not assembled only when you have the entire system and these conditions in place. That's what multi-causal means. The Cartesian product is polycomputable, which means that we can take the same set W, X, Y, Z, and we can see it providing different answers to different questions all at the same time. So it can be the efficient Cartesian product over on the left here, or we can do some different assignment and kind of get different answers from the same set. So math is very polycomputable. So with that all in mind, we're going to move on to history and mathematics. And to give just a little bit of intuition where this idea comes from, in the physical world, goals are constructed through historical processes. I take a lot of inspiration from Esther Thalin and her work on the A not B error, where I think she showed this very clearly, so I encourage you to look that up, or send me an email if you'd like some more information about that. And I think the same is true in mathematics. Goals are not prescribed to mathematical objects, but are built out of relationships between them, and that's how we'll see a very clear sense of history in mathematics. And so to see what I mean, we're actually going to consider a new example, which is the natural numbers. And the natural numbers are also going to be defined by a goal, not by the elements, which is, that goal is counting. So that's what we do with the natural numbers. We count wherever we go, 1, 2, 3, etc. And normally that's the set we think of as the natural numbers, which is just 1, 2, 3, etc. However, there are many other sets that also can count the same way. So let's just call some set, let's say it's M for the natural numbers, which is like a stupid version of the natural numbers. We could count with like the symbols meep, schmlep, blorp, which are just random nonsense symbols, but you can clearly count with them by just going ba, 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 all the way down, for as far as you want to go, and you're still counting. So it's not the symbols that we're using, it's not the specific set, just like with A times B, it's really about the sort of function they fulfill. We could even take a sort of weird version of the natural numbers and count out of order with them, like 3, 1, 567, etc. And we're still counting because it's just about going from the first one to the next one to the next one out of that. So there's a lot of different sets and a lot of different ways to arrange these sets to all do the same function, which is counting. So to see this a little more explicitly, just like with the Cartesian product, we can think of our goal as being to fill out the Cartesian plane in an efficient way. We can think of our goal with the natural numbers is to fill out a counting hand, like we use our fingers to count. We're just trying to fill out each of the fingers in a particular way. Just imagine that you have infinite fingers, so you can fit all the natural numbers onto them. But the way this would work is we would have 1 on the first finger, or we could use the symbol meep, or we could use the symbol 3. It does not matter, as long as we assign one element to this finger and then one element to this finger. So the natural numbers would assign 2, the M for natural numbers would assign schmlep. Then we could be weird with the natural numbers and assign 1 to it. That's all fine. Or we could do 3, blorp, and 567. And the way we show that we're counting the same way with all of these is, again, to use a unique isomorphism, which I've denoted with these colors. Any elements that have the same colors would be mapped to each other, and that would give you a unique isomorphism. That's saying 1 is doing the same job as meep, which is doing the same job as 3, which is, say, they're being assigned to the thumb, and then 2 is doing the same job as schmlep, which is doing the same job as 1, which means assigned to the index finger. 3 is doing the same job as blorp, doing the same job as 567, which is assigned to the middle finger. This is just a way of being formal about saying we're doing the same job with each of these numbers. Just like with the Cartesian product, our counting numbers, our natural numbers, are relationally real, multi-causal, and polycomputable. So if you think about it, the natural numbers and the weird natural numbers are actually equal sets because sets are unordered. So what distinguishes these two sets is the order we assign to the elements here. And we can denote those orders very simply with just arrows. So the regular way we use the natural numbers is just 1 is followed by 2, is followed by 3, etc. But we could also do so differently, like 3 is followed by 1, is followed by 567, etc. Those are both valid uses as indicated by this unique isomorphism. So just like with the Cartesian product, we have things being relationally real. What makes the number 2 the number 2 isn't the symbol. Symbol doesn't matter. What matters is the relationship it has with the number before it and the numbers after it. Its position in that order, that system of relationships, is what makes it 2. It's multi-causal because 2 is never 2 on its own. You need the whole system of natural numbers there for 2 to be occupying the position that makes it 2. And it's polycomputable because the same number can give you different answers depending on how we're trying to use it. Like, is 1 the first number? Well, it is if we use it to be, or we could use it to be the second number, or we could use it to be the 10,000th number. Doesn't matter at all. So with this in mind, what I'm going to say that history is history is the full set of relationships that defines the object. So if we consider the number 50, for example, then 50 in this context is precisely the number that is bigger than 49, and it's bigger than 48, and it's bigger than 47, going all the way down to 1, and is smaller than 51, and is smaller than 52, and is smaller than 53. All of that together is what makes the number 50 exactly 50. So what's interesting about this is this gives us, I think, a very clear sense of history, because if you're constructing the natural numbers, you just count up 1, 2, 3, etc. And so you would get to 50 by just taking the successor of the previous number 49, just saying 49 plus 1 is 50, that's how we get to 50. But the way we actually define 50, what actually makes 50 the number 50, is all of the relationships that come before and after it. 49 is not enough to make 50 50. You need to have 48 there, and 47 and 46 all the way down to 1. And you need to have 51, 52, 53 coming out of it. So that's what coming after it. So that's what history is. It's the full set of relationships that define the object and make 50 exactly what it needs to be. And so with this in mind, we can consider the historical construction of the Cartesian product. this is where we'll really see normativity and preference orders enter things in a major way. So just as a reminder, this is the system of relationships that defines our Cartesian product, where S is any 4-element set that's being used to efficiently fill out the Cartesian plane. But of course, it's not just S. Any set can be the Cartesian product, or can be used to be. So what we have depicted here are 6 different ways of trying to be the Cartesian product. Over in the upper left here, we have the actual set A times B being used efficiently. Over here, we have the set W, X, Y, Z also being used efficiently. Then we have some suboptimal uses, this 3-element set. It can try to do the job, it just does it poorly. We have this 5-element set that's also trying to do the job, but it's just bad at it. We have a 4-element set that could have been used to do the job efficiently, but we didn't use it that way. We assigned everything to just this one point. And here we even have the empty set, which has no elements, which can also be used to fill out the Cartesian plane in a suboptimal manner, which just looks like doing nothing, because that's all we're doing. So with these 6 different ways, and of course there's an infinite number of sets, because all sets can be used to try to be the Cartesian product, whether efficiently or inefficiently, we can consider which one's our favorite, which one is the best one. We're getting normative here. We're going to talk about preference orders. So preference orders is a very simple concept in economics, where you just basically take your list of objects and you say, I'm going to arrange them from least favorite to most favorite. So we can take 3 ice cream flavors. Maybe you like strawberry, you don't like it any more than vanilla. You don't like it anymore, which you don't like any more than chocolate. That's what these symbols means. It means chocolate is at least as preferred as vanilla. Vanilla is at least as preferred as strawberry. Or reading the other way, this could be read as saying strawberry is preferred no more than vanilla, which is preferred no more than chocolate. Now they could actually be equally preferred. So this symbol may look like less than or equals to, should be pretty similar. So this means that vanilla could be equal in preference to chocolate. It's just not more than chocolate. Similarly, strawberry could be equal to vanilla, but it's just definitely not more than vanilla. And we can similarly arrange a preference order between our Cartesian products. So we could say, okay, this inefficient use of the Cartesian product, is not more preferred than this efficient use, which is not more preferred than this also efficient use. So we can clearly arrange Cartesian products into a preference order. And we can be a little more explicit about what that preference order is based on. So for ice cream, we're talking about how much we like to eat the ice cream. So strawberry is liked no more than vanilla, which is liked no more than chocolate. But in terms of our Cartesian products, we actually are going to want to compare them formally with an isomorphism. So do we have a unique isomorphism between this inefficient Cartesian product and this efficient Cartesian product, saying that they're both used the same way? And the answer is no, because there's no isomorphism from a 3-element set to a 4-element set. But here, there is a unique isomorphism from this set to this set, because they're both 4 elements, and there's a very clear way to compare them, where W gets mapped to A1, B1, X gets mapped to A1, B2, etc. So this is what our preference is based on. If you have a unique isomorphism to each other, saying you're both used the same way to efficiently do the Cartesian product, then you're equally preferred. Otherwise, if you're not, then you're less preferred. So with this in mind, if we consider S and S2 and S3 to represent all the other sets that could potentially try to be a Cartesian product, then we can build up this cone here, showing all the comparisons down to A cross B. And this is going to be our historical construction, basically. It's all of these relationships, which aren't historical in a sense of time necessarily, but it's just this full system of relationships, just like our natural numbers, that's really going to ultimately end up defining the Cartesian product. And you'll notice that this ordering, it's a preference order, so we're actually defining the Cartesian product. Historically, it's actually a normative construction. It's about what we like best. So let's be, we're going to basically flatten this comparison to make it even clearer what's going on, which is there's really only 3 layers we need to concern ourselves with. The worst layer is all the inefficient Cartesian products, 3 elements, 5 elements, or a 4-element set that is being misused. All of these are not more preferred, which is to say they do not have unique isomorphism with a set that is being used to efficiently fill out the Cartesian plane, which is not more preferred, or well, in this case is really equally preferred, but we'll still write it this way because it does have a unique isomorphism with our North Star, our sort of pointer, our guiding template for for how we should be thinking about the Cartesian product. And so these are the only three layers. There's inefficiency, there's efficiency, and there's our North Star guiding template. And so what this looks like is this very simple sort of three-layer cake. We have the Cartesian product with its projection functions f and g to a and b. We have all of the other four element sets being properly used. We consider all of them on this layer. They all have a unique isomorphism to a times b, saying here's the exact way in which the four element set is being used to fill out the Cartesian plane in a manner analogous to a times b. And then up here, you just have all other sets which are just not being used to fill out the Cartesian plane efficiently, either because they can't, because they don't have the right number of elements, or because they are being misused. And this is a preference order, as we can denote with these preference relation symbols turned upside down. This is not more preferred than this, is not more preferred than this. So this is a preference order, and this is precisely the historical construction of the Cartesian product. So if you ask, what is the full system of relationships that makes the Cartesian product what it is? It's what's depicted in this graph here, and what's depicted in this graph or in this chart is a preference order. So it is a historical construction that actually gives us a normative outcome. This a times b, it is the peak of the preference order, it is the most preferred option, and that is precisely what makes it the Cartesian product. So it's not what you might think of as a sort of traditionally purely logical situation. It is normative, it is the most preferred option constructed historically. With this in mind, I think it's interesting to just briefly discuss the possibility that functions behave as a cognitive glue for mathematics. Not that they're necessarily the only cognitive glue, but it's interesting to explore this concept. So a cognitive glue should do two important things. It should control the morphology of the system, like how Michael Levin can use bioelectricity to get a flatworm to have like two different heads or something like that. And a cognitive glue should be able to scale up the goals and competencies of the member of the system. And this is exactly what we've just seen functions do. So first of all, regarding morphology, our set a times b is just a generic unordered set. It just consists of these four elements. These four elements do not actually intrinsically have a place on a Cartesian plane, but through functions, they do then acquire this morphology where they efficiently fill out the Cartesian plane. They have this new shape, this new structure through functions, as indicated here. The functions f and g are what it really means to assign these elements to these points. So functions are doing exactly what we would expect a cognitive glue to do. They are controlling the morphology of the system. Additionally, functions are also scaling our system. They are giving goals to elements that would otherwise not have them. On its own, a four-element set does not intrinsically want to fill out the Cartesian plane. It just kind of sits there and does nothing. It's a four-element set. But through these functions, as indicated here, any set that has four elements and has this isomorphism could suddenly, have this goal of filling out the Cartesian plane. So functions, again, we can see them as scaling up the goals and competencies of the system in exactly the way we'd expect a cognitive glue to. So that all brings me to the end of this talk. Thank you very much for your time and your patience sitting through this. I want to just summarize a few points here. The first is that math has properties we ordinarily assign to agents, such as goals. Those goals are relationally real, multi-causal, and polycomputable. So relationally real means it's made out of relationships. Multi-causal means you need to have all of the elements of the system in place to see the property that you're looking for. Polycomputable means that the same elements can give you different answers to different questions all at the same time. Those goals are constructed through a historical process, where the historical process is basically the full system of relationships that fully defines the object, like how the number 50 is defined by all the numbers smaller than in it from 1 to 49, as well as all the numbers bigger than it from 51 to infinity. And finally, relationships between mathematical objects, such as functions, are responsible for the construction of goals and problem-solving abilities that are not attributable to any of the individual mathematical objects. So functions, and perhaps relationships more generally, behave as cognitive glues, and they get something that very much has the flavor of a collective intelligence, where all the parts of the system start doing things in connection to each other that they would never normally do on their own. And the entire system seems to have competencies and goals that are not attributable to any of the parts. So with that in mind, this brings me to the end of the talk. Again, thank you very much.